So in this video, we're going to be looking at intermolecular forces. Right now, before we do that, let's recap some bonding, the different types of bonding, and hence the structures that we can actually get, which are two actual different things. Now, when we look at bonding, right, we need to think about bonding between atoms itself. And when we look at intermolecular forces, we're looking at the bonding between molecules. So it's not really bonding, it's more of an attraction, to be honest, right? Now, starting off, ionic bonding, we know, of course, that's a strong electrostatic attraction between oppositely charged ions, and the structure that we get out of it is going to be a giant ionic lattice. Now, the term giant just basically means it's massive. We've got millions of ions. Ionic is, of course, the type of bonding that we've got between these ions, and then, of course, lattice is this regular repeating structure itself. Now you can see here I've got three different examples. I've got sodium chloride, magnesium bromide, aluminium chloride. Normally we tell we've got ionic bonding if we've got a metal and a non-metal, but in some cases you might actually end up with two non-metals, right? You might end up with molecular ions, like let's say ammonium nitrate is a really good example of one. NH4 and then NO3 itself. So you end up with something that looks like this. Now, of course, you just need to check, have you actually got ions to begin with? And if they're oppositely charged and they're attracting each other, then you know you've got ionic bonding, and hence you've got a giant ionic lattice structure as well. Now, looking at metallic bonding, we know that that is the electrostatic attraction between the positive metal ion and the delocalized electrons itself, and of course we get the structure of a giant metallic lattice itself. Again, just as before, it's a massive structure and it's kind of regular and repeating again and again and again. Again, some examples we can get is, of course, just our plain simple metals like sodium, magnesium, aluminium, and even our alloys as well. Now, of course, covalent bonding is a hard one because that one you can get it mixed up in terms of its structure. We know the bonding between the actual atoms itself. We draw this little Venn diagram and we say it's a shared pair of electrons. Dative covalent bonding, though, that's a shared pair of electrons where both electrons come from one atom. In terms of the giant covalent lattice structure that we can get, we need to remember these four over here of carbon, silicon, boron, and silicon dioxide, where we end up with this massive kind of repeating structure. And of course, we've got lots of these strong covalent bonds, and the boiling and melting point relies on those strong covalent bonds itself. But then, of course, if we were to look at simple molecules, which you might have come across as simple molecular at GCSE, at A level, we say simple covalent. If we were to deal with a simple covalent lattice structure, where we've got a simple molecule or just a basic molecule on its own, so this carbon dioxide, that's going to exist as, of course, one molecule of C and then two lots of oxygen. But then if we were to compare it to diamond's massive. There's millions of carbon atoms bonded together with strong covalent bonds. Yeah. Other examples you can get is bromine, nitrogen, oxygen, water, and then ammonia. Now, why is it important to know the difference between these two? Well, of course, if we were to look at covalent bonding, right, the bonding itself between these atoms within the molecules, we know, of course, it's going to be covalent. Yeah. So this bond between, let's say, this example of chlorine is going to be a covalent bond. But then when we look at the boiling and melting point, we're not actually breaking these chlorine-chlorine bonds. Instead, what we're doing is we're overcoming the attraction between this chlorine molecule here and another one itself. Now, this attraction between this molecule here and the other molecule over here, we refer to that as a intermolecular force, which again, it's something that you've already done at GCSE itself. Now, of course, this intermolecular force, depending upon how strong it is, it will decide what the melting and boiling point is going to be for chlorine. Now, the thing is, with intermolecular forces, they are much weaker compared to metallic, ionic, and covalent bonding. And so we can actually rank the three different types of intermolecular forces that we need to know about in A-level chemistry in terms of the strongest to the weakest. Notice how I've used "est" at the end because we're comparing the intermolecular forces. Overall, they are weak, but then we can compare the strengths of each one of them. Now, of course, at the top of the kind of chart, we end up with hydrogen bonding, which you've come across in A-level biology. And of course, we've got hydrogen bonding being the strongest. It's still weak compared to the other types of bonding like ionic and metallic, but of course, hydrogen bonding is the strongest out of the three. And of course, the next one after that is going to be permanent dipole-dipole interactions, which is going to be the kind of intermediate force between the molecules. It's got medium strength strength, and then induced dipole-dipole interactions, that's going to be the weakest intermolecular force, right, out of the three. So yeah, if we were to look at our simple molecules, our compounds that exist as molecules are not giant covalent lattice structures. They exhibit these intermolecular forces, at least one of them. So yeah, starting off with our first one, we're going to look at permanent dipole-dipole interactions. And permanent dipole-dipole interactions, it's in the name. A permanent dipole, we already know it's when you've got a partially positive charge here, partially negative charge here, because chlorine in this case is going to be more electronegative. It's got a greater ability to attract electrons in a covalent bond, and that dipole, we say it's a permanent dipole. Now, of course, when we look at intermolecular forces, we've got to think about how this hydrogen chloride attracts another molecule of hydrogen chloride. And when you look at it, you've got to think about this in terms of magnets, where you've got a positive charge and you've got a negative charge. Of course, we know that opposites attract in terms of magnets. Think about this molecule over here, hydrogen chloride, delta plus here, delta minus there. This one's going to be delta plus here, delta minus there. You stick them next to each other, and what happens is you end up with an attraction between the molecules. That is one type of intermolecular force, which is what we call a permanent dipole-dipole interaction. Now, in the exam, you need to describe a permanent dipole-dipole interaction as being the intermolecular forces that exist because the difference in electronegativities in a polar bond causes a weak electrostatic force of attraction between the molecules itself. Now, when you see this word here of electrostatic, you've got to think about positives attracting negatives. So in this case here, you've got hydrogen chloride, two molecules, and they're attracted together by electrostatic attraction. Now, normally when we look at permanent dipole-dipole interactions, a rule that we establish is that if the molecule itself is going to be polar, then it will have a permanent dipole-dipole interaction between the actual molecules itself, right? So we first establish, is the molecule polar? If it is, then it is going to have, of course, a permanent dipole-dipole interaction. Now, of course, the strength of this permanent dipole-dipole interaction will depend upon how polar this bond or this molecule will be. Now, of course, if the molecule is more polar, then the strength of the permanent dipole-dipole interactions is going to be greater itself. So moving on, right, we can actually get a specific case of permanent dipole-dipole interactions where we're dealing with an OH, FH or an NH bond, and this is actually called hydrogen bonding, and this is the strongest intermolecular force that you'll be dealing with. Now, of course, if I were to look at an OH bond as an example, FH and NH, they follow the same thing. We already know oxygen is going to be the more electronegative atom. We know, of course, with the electrons in this covalent bond over here, they're going to be attracted more towards the oxygen atom, and that creates a dipole where I end up with delta negative for oxygen and then delta positive for hydrogen itself. Now, of course, because oxygen, fluorine and nitrogen are very electronegative, their strength in terms of attracting electrons in a covalent bond is going to be very high. They're pulled more towards the actual oxygen itself, and so we end up with a very polar bond. And of course, that now leads to a new specific case of permanent dipole-dipole interactions, which is what we're calling hydrogen bonding, right? Now, just be sure when you use this word in the exam, hydrogen bonding, you don't use the word H bonds, because that is not accepted in chemistry. It's only accepted in biology itself. Yeah. Now, of course, you need to be able to draw a diagram from this, as well as recognize that you've got hydrogen bonding between molecules. Good examples include water, ammonia, hydrogen fluoride, any alcohols that you might deal with in module 4. Now, when it comes to drawing a diagram, what I like to do is, of course, add on my partial charges, my lone pairs, both of them on the oxygen because it's got two, and then of course a partial charge on hydrogen as well. Now there is of course our first actual molecule of water dealt with. How do I actually draw the rest of my diagram out? Well, I like to add a dashed line to my actual hydrogen here, and that's going to be attracting another partially negative oxygen. It's going to actually go towards a lone pair on another oxygen atom. So you can see here I've got two lone pairs on there. It needs to come from one to get right in the exam, and of course I'm going to end up with my hydrogens bonded to the oxygen, and then my partial charge is delta plus, delta negative, and then delta plus over here. That's how I like to draw it out. It just makes sure that I get it right in the exam every single time. Now the next thing I need is of course a label, and I need to tell the examiner that this dashed line is not just there for design. That is actually called a hydrogen bond itself, right? And there's 2 marks there in the exam. So yeah, there's my hydrogen bonding diagram. I want you to have a go at the following two examples. I want you to draw a hydrogen bonding diagram for ammonia and then one for hydrogen fluoride, following the steps that of course we did in the worked example itself. Feel free to pause the video and have a go at the following. So you're looking at this one. I've got ammonia. The first thing is I know ammonia is going to have one lone pair on there. I'm going to have a delta negative for the nitrogen. And of course, I've got delta positive here, delta positive there, and then delta positive there. Now, of course, we know this NH bond, it's going to be polar. It's going to have hydrogen bonding because it's one of NH, FH, or OH bonds. I'm going to end up with my dashed line. I'm going to draw about 4 or 5 of them. I'm going to draw 4. And then that's going to the lone pair on another actual ammonia molecule. So, of course, I've got nitrogen here, bonded to a hydrogen, bonded to another hydrogen, bonded to another hydrogen here. And I'm going to have delta negative, delta positive here as well, and then delta positive there. That's one mark so far. The next mark is, of course, we need to label this bond and say that we've actually got a hydrogen bond itself. Looking at the next one then, because there's 2 marks there so far. Using a diagram, we need to show the hydrogen bonding between 2 molecules of HF. Now, hydrogen fluoride, we know it's going to be a HF bond. So in that case, it's going to have hydrogen bonding. We know fluorine actually has 3 lone pairs on it. So I'm going to draw each one of them out. I've got a delta plus sign for hydrogen, delta negative sign for fluorine, and I'm going to draw my actual lone pair, a kind of dashed line going towards the right in this case, because that seems to be easier, about 4 of them, and that's going to a hydrogen in this case. That's going to be delta positive, and then of course we've got that bonded to fluorine, which is delta negative, but don't forget your lone pairs on there as well. You've got 3 pairs of lone pairs. I need a label, and I'm going to say that that is going to be my hydrogen, and then it's going to be bond itself. And there's another 2 marks for that example over there. Just make sure when you do these that you've got the fluorine forming a hydrogen bond to a hydrogen itself, because that's how hydrogen bonding actually works. Now, moving on then, if we were to look at hydrogen bonding in a bit more detail, we need to be aware of 2 anomalous properties. The first one is ice is less dense than water. Normally, when we look at densities, when we have a liquid, we know it's not very dense, the particles aren't packed together, and of course, they're kind of free-flowing and they move about and they fill the shape of a container. But then, when we go to form a solid, we end up with a very dense structure where they're closely packed together. Now, in the case of water, we don't actually have that, because of course rather what we have instead is our hydrogen bonding actually holding our water molecules apart. So what we end up with is a less dense structure, and that's why water actually expands when you freeze it. It actually gets bigger, right? You can try this at home if you have a carton of any juice or anything like that. You put it in the freezer and then it actually swells up itself. So ice is less dense than water. Why? Because hydrogen bonding holds water molecules apart. Now the next one is ice actually has a relatively high melting point, and again the reason for that is going to be because hydrogen bonds, they're going to be relatively strong compared to other intermolecular forces, right? So yeah, of course it's relatively high compared to anything else that you deal with, like a molecule like chlorine, bromine, or even things like your alkanes like methane and stuff as well. Now, another thing that you need to be able to do in the exam is you need to be able to compare the strength of a hydrogen bond. You can see I've got here 2 compounds. On the left hand side, I've got a compound called ethylamine, which you look at in module 6. And then I've got here ethanol, which of course you've done at GCSE. If you haven't, you look at it in module 4. Now, of course, nitrogen here has 1 lone pair. Oxygen here, it actually has 2 lone pairs itself. And when we compare these 2 structures, right, we've got to think about the strength of the hydrogen bonding between the molecules. Now, ethanol actually has a higher boiling point compared to ethylamine. And the reason why, the first reason, is that the oxygen atom is going to be more electronegative than the actual nitrogen atom itself, right? Another reason is because this oxygen atom over here has more lone pairs than the actual nitrogen atom itself. Nitrogen has 1, oxygen has 2. Therefore, ethanol is going to end up with stronger hydrogen bonding. And a key word we always need to remember is between molecules itself, because remember, we need to keep referring to it as an intermolecular force. So yeah, this requires overall more energy to overcome. Now let's say if I were to deal with fluorine, fluorine is going to be the most electronegative, and it has 3 lone pairs on it. So just in case you come across that example, there's that there as well. So moving on then, looking at our final intermolecular force, we're looking at induced dipole-dipole interactions. In other words, London forces. That's what the examiner likes to use as well. They can use either one of them, but I prefer induced dipole-dipole interactions. This happens in every molecule, regardless if it's polar or non-polar. Now just remember, in a molecule you can end up with more than one type of intermolecular force, but we normally describe the strongest one when we're comparing boiling and melting points. Now induced dipole-dipole interactions, in the exam, we need to be able to describe and explain how these are actually formed, right? Now, in a nutshell, basically, imagine you've got an atom and that atom actually contains electrons. If I've got, let's say, 54 electrons for an atom of xenon, because the atomic number is 54, we know, of course, in xenon, we've got a positive nucleus and then we've got our shells, and these electrons, they're going to be whizzing around, they're going to be moving around constantly. Now, of course, at a given moment in time, what will actually happen is we create something called an instantaneous dipole, and that's when we end up with an uneven distribution of electrons, where I would end up with, let's say in this case, I've got my positive charge over here. I've got, let's say, on one side of my actual atom itself, I've got, let's say, 50 electrons, and on the other side I've actually got 4 electrons. Now, of course, because of this uneven distribution of charge, if I've got 50 negative electrons on one side and only 4 negative electrons on the left side, I can actually assign a partially negative charge on this side here and a partially positive charge on this side over here. Now, of course, we call this an instantaneous dipole, and this happens across the molecule or the atom itself. Now, of course, we've got this instantaneous dipole, and let's say that this is going to be atom 1 of xenon. Now, let's say if I've got another atom of xenon, where of course we've got a positive nucleus again, our electrons are going to be whizzing around. Now, this actual instantaneous dipole that we can see over here is going to actually repel the electrons in another atom, because of course we've got this partially negative side with 50 electrons. These electrons, this electron-rich area, is going to repel electrons in another molecule, and so it creates dipole in this molecule itself. Now, if all the electrons move to this side over here, where we end up with, again, a similar distribution of electrons, where I could end up with, let's say, 50 electrons on this right-hand side here, and then 4 electrons on this side over here, what we've basically done is we've induced a dipole into this neighboring actual atom itself. Now, of course, that starts some sort of a chain reaction, where that will go on to induce a dipole in another neighboring molecule. It will induce a dipole into another one, and then that will induce a dipole into another one, and so on, up until a point where we actually end up with lots of these temporary dipoles itself. And now the thing is, let's say if I were to stick these two together, you might notice something, and that is that we've got a partially positive charge here, a partially negative charge there, and they're going to attract. The attraction is only weak. That's why we say that these are the weakest out of all of them, because it's not a permanent dipole. Instead, it's a temporary one. That's why we say the intermolecular force is called an induced dipole-dipole interaction itself. These small induced dipole-dipole interactions, they're going to attract one another, and they cause a weak intermolecular force themselves. Now, looking at this in terms of how we describe it in the exam, there's a bunch of points we need to mention, and we kind of just memorize it and we learn it, but we need to know that every molecule actually exhibits this. Now, the first point we need to mention is that induced dipole-dipole interactions are caused by the movement of electrons within the shells. This causes an instantaneous dipole across the molecule, so that's what you can see. We've got the movement here, and then the causing of an instantaneous dipole over here. The instantaneous dipole in one molecule, this is inducing a dipole in a neighboring molecule, which induces another and another and another, and so on. And then overall, we end up with them attracting, and this causes a weak intermolecular force. Now, of course, this is just about 3 or 4 marks that you need to learn for the exam itself. Yeah, just be aware of that. Now, moving on, we do need to compare the strength of our actual induced dipole-dipole interactions in different atoms, in different molecules. Now, I can take 2 examples. Let's say if I were to look at something like fluorine, which is F2, and then if I were to take something like, let's say, iodine, which is I2. Iodine, I know I've got 53 electrons in total, whereas if I look at fluorine, it's got 9 electrons in total. Now fluorine is going to be a gas at room temperature and pressure. Iodine is going to be a solid, but of course that vaporizes quite easily. Now when we look at the difference between the two, they've both got the same number of atoms, but if you look at the difference, iodine's got a lot more electrons. It's a lot larger, it's bigger, and if an atom contains more electrons and if it's larger, we know that the strength of the actual induced dipole-dipole interactions is going to increase. Because think about that uneven distribution of electrons. Let's say if I were to look at the top one, we've got fluorine, we've got 9 electrons, so we can end up with, of course, an induced dipole, and of course we would end up with that attracting another one. But if you look at our distribution of electrons, we've got 3 electrons versus something like 6 electrons, and that's attracting, of course, another kind of molecule, although it is partially negative here and then partially positive there. Same thing over here, partially positive there, partially negative over here. I've got 3 electrons and then 6 electrons there. The attraction is quite weak compared to something massive like iodine itself. This is going to be stronger in terms of attraction, because if you were to think about it, the distribution of electrons is going to be larger itself as well. Yeah, so if I were to look at this one, I could have, let's say, 50 electrons on one side. That's the delta negative side. We end up with, of course, a greater kind of partial negative charge in a way. And then on this side, we end up with, of course, 3 electrons itself again. And that's going to be delta positive. Yeah. And that's going to be attracting a delta positive, delta negative again. We've got 3 electrons here versus 50 electrons over there. So we can see here, we've got a greater partial negative charge compared to this one over here. So yeah, what do we need to say in the exam? Well, if we have a larger atom, we have more electrons, stronger induced dipole-dipole interactions between the molecules, and that requires more energy to overcome. Now, the same thing happens if you've got a larger surface area, if you've got a larger molecule where you've got, let's say, something like pentane, and you were to compare pentane to something like ethane, you know, of course, pentane is going to have lots of interactions between the surfaces of it and another molecule compared to ethane, which is going to have very few interactions. And that's why in organic chemistry, as the carbon chain length increases, the strength of the induced dipole-dipole interactions increases, and that requires more energy to overcome itself. So yeah, to summarize, how do I actually tell what type of intermolecular force I've got? Well, I look at it, is it a molecule to begin with? If the molecule's non-polar, the strongest intermolecular force we have is an induced dipole-dipole interaction only. Now, if the molecule's polar, we still have induced dipole-dipole interactions, but if it contains no FH, NH, or OH bonds and it's polar, it has induced dipole-dipole interactions, yes, but it also has a stronger one, which is permanent dipole-dipole interactions. If it does contain FH, NH, or OH bonds, then we say it's got, yes, still induced dipole-dipole interactions, but it has the strongest intermolecular force, which is hydrogen bonding as well. So moving on then, I've got a final task for you to do. I want you to compare the actual boiling and melting points of the following compounds. More importantly, I just want the explanation for each one of them. Feel free to pause the video and resume once you're ready to move on. So yeah, in terms of phosphine versus F2, we need to decide first of all, are they going to be, of course, polar to begin with? Phosphine versus fluorine. Well, fluorine, that's going to be non-polar because we don't have 2 atoms of different electronegativities, of course, attached to each other. We know the strongest intermolecular force is going to be induced dipole-dipole interactions. If I were to look at phosphine though, phosphine, we know it has a shape where, of course, we've got a hydrogen here in the plane, we've got a lone pair there, we've got, of course, a hydrogen coming towards us, and then, of course, we've got a hydrogen that's coming away from us as well. We know, of course, the hydrogens are partially positive, 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 and the phosphorus is partially negative. We've got an overall dipole, which is going to be pointing upwards, and, of course, a positive side to it as well. Now, this molecule is polar, but it doesn't contain FH, OH, or NH bonds, so it doesn't have hydrogen bonding, but it does have permanent dipole-dipole interactions. So we know permanent dipole-dipole interactions are stronger than induced dipole-dipole interactions. So in that case, here's what we need to say. We need to say that phosphine has permanent dipole-dipole interactions between molecules, and that between molecules bit is very important because a lot of people forget that. It's required in the exam. Fluorine has only induced dipole-dipole interactions between molecules again, and then of course permanent dipole-dipole interactions are stronger and require more energy to overcome. Yeah. What about the next one? Well, we've got ammonia versus, of course, phosphine. Phosphine, we already know it's polar. It's got permanent dipole-dipole interactions. But ammonia, we know it's going to be a polar molecule. It's going to look something like this, wedged and dashed bonds included. We know that's going to be, of course, lone pair there, delta negative, delta positive, positive here, positive there. There is an overall dipole, but more importantly, we've got an NH bond in there. That means we've got hydrogen bonding. Now, of course, hydrogen bonding is stronger than, of course, permanent dipole-dipole interactions. So what do we need to say in the exam? We need to tell the examiner that ammonia has hydrogen bonding between molecules. Phosphine has permanent dipole-dipole interactions between molecules. Hydrogen bonding, though, is stronger and requires more energy to overcome. You can kind of see the pattern to how we word these questions. So looking at the next one, we've got hydrogen iodide versus hydrogen bromide. Now we know both of these do have permanent dipole-dipole interactions because they're both just polar bond containing molecules, and they only consist of one bond, so we know the entire molecule is polar. They also have induced dipole-dipole interactions, but the strength of the induced dipole-dipole interactions is going to be different, right? Now, of course, if we were to look at it, hydrogen iodide itself, because this came up as an exam question, that contains iodine, and that has 53 electrons itself. But then if I look at bromine in hydrogen bromide, the bromine atom actually contains 35 electrons itself. So if you compare the two, we know hydrogen iodide is larger, contains more electrons, and therefore has stronger induced dipole-dipole interactions between the molecules, and that requires more energy to overcome. Now here's what we need to be able to say in the exam. Of course, hydrogen iodide is larger and has more electrons than HBr. Hydrogen iodide has a stronger induced dipole-dipole interactions between molecules, and that requires more energy to overcome. There's 3 marks there. Don't forget the between molecules in all of these.